Swayam Prabha. Digital India. Educated India.
All right, good. So let us get started. So yesterday we left at this slide. We sort of completed Michaelis-Menten equation. So Michaelis-Menten equation relates the rate of the reaction with these important terms like substrate concentration, the maximum velocity that is possible for a given enzyme at saturating substrate concentration, and then the Km. Okay. So today what we are going to do is we are going to have a look at these two terms, Vmax and Km. So the main picture that you need to keep in mind is we are trying to do all of this to get an idea of how good an enzyme is. So how do you define good for an enzyme? How much rate acceleration can it do compared to the uncatalyzed reaction? So that is one. As a catalyst, how great it is. And second, to achieve that sort of a catalytic enhancement, rate enhancement, what kind of substrate concentration does it need? Can it do even at very low substrate concentration? So combining these two is how you measure and define how good an enzyme is. Okay, so that is what we are getting at once we have understood how to measure the rate of the reaction. Okay, so this equation and trying to understand what Km tells, what Vmax tells, etc., is to get an idea of how great an enzyme is, a given enzyme is. Okay, so keep that in mind. Then our discussions today will make better sense. So first thing is we are trying to see in the graph that we saw yesterday a simple plot of rate versus the substrate concentration, where at a high substrate concentration the rate saturates, reaches a maximum, it plateaus off due to enzyme getting saturated with the substrate. So in this graph we are going to look at how this equation performs in this graph. So let us look at the early phase. In the early phase, your substrate concentration is extremely low, like if you take this portion, and therefore Km is probably a lot greater than substrate, and we can compare to the Km value, S may be ignored. And if you are going to ignore S, then this equation becomes like this. So these two are going to be constants. That means velocity is going to vary linearly with respect to substrate. As substrate increases, V0 increases. So you see linear relationship in this region of this graph. Okay, and this is extrapolation. But we need not worry about the extrapolation. For us, in this low substrate concentration, yes, it does increase linearly. And that is what this equation tells us. Okay, now what happens when it goes to the other end? In the other end, you're going to have substrate lot higher than Km, and therefore Km can be ignored. And if you don't have Km, then these two S cancels, then V0 equals Vmax, and these two being constant, it is going to remain the same. So now velocity is no longer going to be a function of the substrate. Okay, because that does not figure in the equation anymore. So at least in this graph for a simple enzyme, this Michaelis-Menten equation holds well. Okay. So having done that, now we look at another important relationship that the Michaelis-Menten equation reveals, and that is the value of Km itself. So now imagine the velocity is roughly about half of the Vmax that is possible. So if V0 therefore equals half of Vmax, then if you substitute that value here as well, then you are going to find that, so if you cancel these two, then half equals S by Km plus, so that eventually tells you that Km is actually S, right? So then only it will be half. So therefore, Km actually is equivalent to the concentration of the substrate when the rate is about half of the maximum rate possible. When V0 equals half Vmax, whatever be the substrate concentration for that, like for example here at this substrate concentration, you reach half the Vmax, and that concentration of substrate equals Km. So therefore Km has units in terms of concentration, okay, equals moles. So this is an important relationship revealed by MM. So when people ask you what is Km, you should be able to tell this. Km equals substrate concentration when V0 equals half Vmax. Okay, so this is an important relationship, and it also helps us to calculate Km very readily. So now this equation can be transformed in multiple ways to focus on one term or the other, or for making accurate calculation of one term or the other in this equation. So one such transformation is shown in the next slide, where we are actually taking double reciprocal of these two terms on both sides, and that is what is here. So you take a reciprocal, so 1 by V0, so this will become Km plus S divided by Vmax. Okay. Now, if you split this up, it becomes like Km by Vmax S plus S by this, so this cancels, then it becomes 1 by Vmax. So this becomes like the equation for a straight line. So, y equals mx plus c. So this is constant, this is c, this is m, Km by Vmax will be s, sorry, m, and this will be 1 by s will be the x. So y equals mx plus c, that's the equation for a straight line. Now going by that, we know the slope. Slope for the straight line will be m, and therefore it is Km by Vmax. The slope of this line is Km by Vmax. And this y-axis intercept will be c in the equation for a linear line, and therefore it is 1 by Vmax. So we do not worry about this intercept and minus 1 by Km. So these two are the really main points, and this is what helps us to measure the Vmax as well as Km very readily. So this double reciprocal plot was this plot was proposed by Lineweaver and Burke, and this is also called Lineweaver-Burke equation. Okay, 1 by V0 equals Km by Vmax S plus 1 by Vmax. This is called double reciprocal equation because you are taking a reciprocal on both sides of the Michaelis-Menten equation, and this makes it easier to plot and very accurately, because it's a linear line. Calculating slope is very easy, and it gives an accurate measurement of Km and Vmax. So this is the equation that practically people use in a lab to evaluate the catalytic efficiency of an enzyme. So now let us look at what the Km and Vmax can tell about an enzyme. So before going into that, here is one small discussion. So Michaelis-Menten kinetics applies to many enzymes regardless of their catalytic mechanisms. That actually is the limitation as well of this steady state kinetics. So I'll tell you in a minute about that. So then Km can vary greatly from enzyme to enzyme and among various substrates for a single enzyme. Suppose a given enzyme has some flexibility in substrate specificity and can actually work on 2 or 3 different substrates. One substrate to another substrate, Km can vary. So here are Km for some of the commonly known enzymes with the given substrate. So this hexokinase is the one that phosphorylates glucose to glucose 6-phosphate. That's the starting step in breaking down glucose to make ATP. So here ATP itself is a substrate because it transfers the phosphate group from ATP to glucose to make glucose 6-phosphate. The version of this enzyme present in brain is hexokinase, and the one that works elsewhere are called glucokinase as well, and that has this sort of concentration for Km value. So let me see what I have. Yeah. So one of the limitations of the steady state kinetics, that is the Michaelis-Menten equation, is a steady state equation because we make that assumption at the beginning. We are measuring initial velocity and then we are measuring at a point where the rate of formation of enzyme substrate complex equals the rate of breakdown of the enzyme substrate complex, that is ES. So here, regardless of the number of steps involved, okay, it doesn't tell how many intermediate steps are involved. Remember, we have considered that enzyme catalyzed reaction can have multiple intermediate steps. Like for example, ES formation is an intermediate step. Probably in some cases ES becomes EP, that is one more intermediate step. Then you have the EP dissociating as enzyme plus product. So there could be multiple intermediate steps. So this does not tell you about how many intermediate steps are there and what is the rate of individual intermediate steps, and it doesn't tell what is the chemical nature of the conversions that are going on. So it doesn't tell any of that. It depends primarily on the rate limiting steps, which we will see in a minute. But nevertheless, it is still very useful to measure the property of an enzyme, so it is still always used. So all other technologies like site-directed mutagenesis, crystallographic, structure determination of enzyme active site, etc., they are all always used in conjunction with this Michaelis-Menten kinetics. So therefore, it is still being used as a major way of measuring enzyme activity. So therefore, it is still very valuable. So let us look at Km under different conditions. So many times, if you particularly look at old textbooks and some really preliminary introductory textbooks, what they will say Km is a measure of the affinity of the enzyme. So higher the affinity, lower the Km, meaning at a low substrate concentration itself, the enzyme can readily bind the substrate. Like 50% of the enzyme will be bound with substrate even at low concentration of S. That's what would be low Km indicating. So therefore, Km indicates affinity of the enzyme for the substrate. This is true under certain conditions. So that is what this slide is trying to tell you. So for example, where K2 is very low, let us say you are looking at the very initial reaction where ES formation and breakdown is the main thing. ES has not yet started producing E plus P. So the K2 will not be a major factor. So if you take out the K2 in this equation, then it is simply, this is the rate of formation of ES, this is the rate of breakdown of ES. So this is E plus S in a reversible equilibrium with ES, which would simply be like a ligand receptor binding. Dissociation constant is what Km will be. Under that condition, obviously this will indicate the affinity. Okay. But this relationship will not be true if K2 is a significant value. If it is significantly large, then it will be a function of all three. And suppose if you have an intermediate step, like for example, you need not even have intermediate step, you will have K minus 2 as well, like E plus P combining to form E plus ES, enzyme substrate complex. So like this, the other side of ES. So it will be Km then will reflect all of those rates, and therefore it will be a complex function. It will not simply be reflecting the affinity of the enzyme. That is the major interpretation of the Km. So, and in many situations, this value being large or this being equal to this, etc., will depend on a given reaction mechanism. So therefore, Km will not simply be equal to affinity of the enzyme for the substrate. So it is true only under certain conditions. But still, it is good idea to remember that Km is an indicative of affinity of the enzyme for substrate, because in many situations that is true, and that assumption helps us to understand many aspects of enzyme kinetics. Because after all, we are defining Km as equal to substrate concentration when V equals 1 by V max. Sorry, half V max. And next, let us look at similarly about Vmax as well, what Vmax tries to tell us. So, yesterday we saw this K1, that is the forward reaction of E combining with substrate is readily, it is faster and readily happens. And this step is the rate limiting step, that is ES getting converted into E plus P. Now, under such situations, K2 will be rate limiting step. Okay, and therefore Vmax will actually depend on K2. So V0 actually reflects this reaction step and not all of them. But on the other hand, let us assume you have one more intermediate step, like in the enzyme, on the enzyme, substrate actually gets converted into product, and you have an enzyme product complex. And that is going to dissociate into E plus P, and that dissociation is slower than all these four reactions. Then Vmax will be, K3 will be rate limiting, and therefore Vmax will be affected by K3. So therefore, what is determining Vmax, therefore will vary which step is rate limiting. And where this leads us to a term called Kcat. So in this particular experiment, K3 is Kcat. And if you have more, K4, K5 and so on, then whichever one is rate limiting, that rate limiting steps rate constant would be the cat. Okay, Kcat. So Kcat is the rate constant for the rate limiting step. In this particular case, K3, in the earlier examples we considered it is K2, which is the rate limiting. So the rate limiting steps rate constant is what is Kcat. And this is an important one. So, the higher the value of this, then the higher the overall rate of the reaction. So in Michaelis-Menten equation, if we go back, so Kcat will be equal to Vmax by Et. That is simply because, let me think. So yeah, so in Michaelis-Menten equation, so you have K2, and that K2 is Vmax by Et, and that if you substitute, then you get this situation. So V0 equals, so now Kcat equals going by this relationship, it will be Kcat time Et will be Vmax, and in Michaelis-Menten equation you substitute that. So in any case, Vmax is always going to be equal to this, because it is not going to increase beyond the total enzyme available, and the rate constant for that, this would always be the Vmax in any situation. And when you have this substituted in the Michaelis-Menten equation, then if you look at different situations, suppose when you are looking initially where S is really low, then it will be V0 equals kcat by km. So this ratio times ETS. So now the substrate concentration will be directly related to this, linearly related to V0. And this term kcat indicates the number of substrate molecules that is converted into product on a single enzyme molecule when the substrate is at a limiting saturating concentration. Okay, so that is another definition. So it's a first order rate constant because it is not dependent on substrate concentration. It is simply Vmax by ET, and as a result, it is a first order rate constant, not dependent on the concentration of the substrate. And this is what you need to really remember. It is equal to the number of substrate molecules converted to product on a single enzyme per unit time when the enzyme is saturated with the substrate. This is an essential condition under which this relationship holds good. So this is also called a turnover number. It is because how many substrates are turned over per unit time. The only additional thing you need to remember is where this is true when substrate is at saturating concentration. So this helps us to measure essentially the rate at which substrate is being converted. And that if you look at for some of the enzymes, it's extraordinarily high, like for catalase that breaks down hydrogen peroxide into water and oxygen. So this one acts at a rate of 40 million hydrogen peroxide molecules per enzyme molecule. Okay, that's what you need to remember. One enzyme molecule converts 40 million H2O2 into products per second. Okay, so that is one of the highest turnover number known. Catalase. This catalase and along with an enzyme called superoxide dismutase, both of them are important in scavenging free radicals generated in many reactions in our cell. Otherwise, the breakdown of H2O2 generating O2 minus, the superoxide radical, reacts with many molecules and causes damage, particularly to membranes, biomembranes. And this is a major issue in the brain. And to take care of it, a subsequent enzyme, superoxide dismutase, converts that into water molecules. So essentially, H2O2 becomes water molecules.